If you've heard anything about the history of our universe, you've probably heard about the Big Bang Theory. But unless you dug a little deeper, you might not have realized that the most important aspects of this theory have nothing to do with a bang at all. And in fact, there may never have been a bang in the first place. In order to understand what the Big Bang Theory is really all about, we need to talk about gravity. And the most accurate theory of gravity that we have today is Einstein's theory of general relativity, which fundamentally transformed the way we think about space itself. Unlike Newton's theory of gravity, where space is a static background in which forces attract masses, general relativity describes space as a dynamical system that interacts with matter by bending, warping, and changing over time. So what does this have to do with the Big Bang? It turns out that if we look at a large volume of the universe in which matter is pretty evenly distributed, general relativity predicts that it will stretch over time, pulling the galaxies within it farther and farther apart. This result was first derived in 1927 by the Belgian priest and astronomer Georges Lemaitre, and it was confirmed by the observations of Edwin Hubble just 2 years later. But this stretching means that if we look back in time, this volume must have been smaller than it is today, and the further back we look, the smaller it must have been. A natural conclusion is that some time ago, 14 billion years if you do the math, this piece of the universe had zero size, something that physicists call a singularity, and it must have just begun to grow out of nowhere, a simple and beautiful origin story that we call the Big Bang. Well, it's simple as long as you don't think too hard about it. In reality, this story would raise a lot of obvious questions, like how can matter fit into a volume of space with no size? And if that really did happen, wouldn't we all just be stuck in a black hole? The truth is, the origin of the universe, if there even was one, probably looked nothing like the singularity described by this theory, because the logic of extrapolating general relativity further and further back in time can only be pushed so far. To see where this logic breaks down, let's pick a chunk of the universe that exists today and try to trace back its history as close as we can get to the point of the Big Bang. Let's say that this chunk is our entire observable universe, a sphere that's centered around the Earth and extends to the farthest points from which light has had time to reach us. The radius of the observable universe today is approximately 46 billion light years. As we go back in time and compress the observable universe, not only does its density increase, but so does its energy, as light waves are compressed to higher frequencies and individual particles gain kinetic energy. Thermodynamics tells us that as all of this is happening, the temperature of the entire observable universe also increases. Even the empty parts of space between galaxies are filled with cosmic microwave background radiation that heats up. By the time the universe is about 300,000 years old, the temperature is so high that atoms themselves are no longer stable. Electrons are separated from nuclei, and the entire universe is a giant mess of plasma. There's no structure here, no planets, no stars, no galaxies, just plasma. But general relativity still works, so let's keep going. When the universe is about a minute old, temperatures are even higher, and nuclei break up into individual protons and neutrons. At this point, the observable universe is smaller in size by a factor of 1,000 than the Milky Way galaxy alone today. But even this far back in time, general relativity still works, and we know it works because these conditions make predictions about what we should observe in the universe today. The structure of the universe, the sizes of galaxies, the relative abundances of hydrogen and helium. And all of these predictions are fantastically accurate with what we actually see. But when the universe was younger than a second old, there are no longer any measurements we've made that can confirm the accuracy of general relativity. We can still suspect it works, but we can't be too sure. An even bigger problem arises when the universe is really in its infancy. If we go back to a time that physicists call the Plum Era, just 10 to the minus 43 seconds after the point of the Big Bang, when the universe is smaller in size than the width of a single strand of human hair, energies are so high that random fluctuations in the gravitational field might arise from quantum mechanics and change the way the universe is evolving. And general relativity doesn't know how to account for these quantum effects. Einstein developed the theory in 1915, a decade before a full theory of quantum mechanics was first developed. Even in the 100 years since then, physicists have been unable to incorporate quantum mechanics into general relativity in a way that can truly describe the universe in this ultra-dense state. As a result, We know that sometime between 1 second and 10 to the minus 43 seconds after the Big Bang, general relativity becomes unreliable, and the stretching of space that Lemaitre predicted can't be played backwards beyond that point. There's been a lot of speculation about what the universe was doing when it was even younger than this. Some hypotheses say it remained small in a state of quantum foam. Other hypotheses say it bounced back and started to grow again. But the truth is, no one really knows. So let's bring all of this together and give a more precise description of what the Big Bang Theory really is. It's a model of our universe that starts out with a hypothetical singularity that didn't actually exist. The singularity spontaneously starts to grow with a Big Bang that didn't actually happen. But after just a fraction of a second, the story of the Big Bang Theory begins to align with the true history of our universe. And from that point forward, the success of the model is indisputable.